Last time, we figured out the reflection and transmission coefficients describing the interface between two materials, and that's a useful thing to be able to do. But it's actually when you have more than two materials that things get really interesting. When you have, for example, three media, one on the left, one on the right, and a slab in the middle of some controllable thickness, that gives you enough free parameters to really start controlling what the light does. And that opens up a whole raft of technological applications, from mirrors to anti-reflection coatings to display text, and so on and so forth. In the pictured setup, we have an incident wave coming in from the left in medium 0 with index n0. We'll indicate its field with an e0. There's also a leftwards traveling reflected wave in that region indicated by e0 double prime. In the middle material, with thickness A and index n1, we have leftwards and rightwards propagating waves, indicated by e1 double prime and e1 prime, respectively. And finally, in the last region, with index n2, we have a transmitted wave e2 prime. Our goal will be to figure out the reflected and transmitted intensities relative to the incident intensities. We have 5 fields, one of which will be known, so we'll need 4 equations to pin everything down. As before, we'll turn to our boundary conditions to generate those equations. And as before, since the light is normally incident, the fields will be oscillating strictly parallel to the interfaces, so only the E parallel and B parallel boundary conditions will be useful. Let's write the plane wave E fields in each region, assuming uniform polarization. Note the same general features as last time. Crossing an interface can't change the frequency of a wave, so these all have the same omega. But each region has its own k vector, k0, k1, or k2, representing shifts in wavelength. And note that the left and middle regions each have both left and right propagating waves, with the direction indicated in the exponential. So let's start cutting this down to size. Everything has the same omega, so when we start invoking boundary conditions like E parallel in one region equals E parallel in another region at some boundary, the fact that each term has the same omega and t means those chunks of the exponential are going to drop out. Everything is uniformly polarized, so all the low polarization vectors are going to drop out. There are 2 boundaries where we can apply the E parallel boundary condition. Let's start with the boundary between regions 0 and 1. That's indicated by x equals 0, so if we put x equals 0 into the fields for regions 0 and regions 1 and set their sums equal to one another, we get. Next up, we can use that same boundary condition, but at the boundary in between regions 1 and 2. There, we're not going to be so lucky as to have the exponentials fall off because x is going to be equal to a. And now we have 2 equations to pin down the 4 unknowns. Next up, we'll apply the boundary condition involving the parallel components of the B field. Once again, making the simplification that in non-conducting materials, the various mu's are generally pretty much the same. I'll go ahead and step all the way back to the basic representations of the B fields. Note once again that I'm being very careful with the directions of the polarizations of the B field. The incident wave is propagating in the I hat direction, and the E field points in the J direction, and so for E cross B to give the propagation direction, the incident B field has a K hat vector on it. The reflected field is propagating in the minus I hat direction and has an E field pointing in the plus J hat direction, so that polarization vector must be in the minus K hat direction for that cross product to work out. We play a similar game in that middle region, and then have a relatively clean expression for the fields in the transmitted region. Now, as before, we can drop all those common polarization vectors, all the K hats, and all the common time dependence. We're going to want to sub in for those B field magnitudes in terms of E field magnitudes. We know that in general, so if we take each B field amplitude and replace it with n times the E field amplitude and drop the common C, we can get the following. Alright, now we are really getting somewhere. The fields in these regions have to be continuous across the various boundaries. So first we look at the x equals 0 boundary and get. And then we look at the x equals a boundary and get. Alright, so that gives us a total of 4 equations. Let me go ahead and write those 4 out for our convenience. 4 equations, 4 unknowns, because we're considering E naught to be known, and that is plenty of information for us to solve for all of the fields and get any reflection and transmission coefficients at either interface. Now that's kind of a brute force approach to the problem. It's often the case that you have a specific application in mind and you can kind of tighten down on your procedure. For example, what if what we really want to do is make it so that there's no reflection off of that first surface? What if we want to learn how to make an anti-reflection coating? To do that, we need E naught double prime to be 0. And that is a thing that comes up all the time in science and engineering applications. So what we're going to do is we're going to simplify these equations by taking them and knocking out E naught double prime. It's still not a completely trivial set of equations, but if we take these things and start mashing them together, we can eventually discover the following condition. Any combination of indices, wavelengths, and thicknesses A that satisfies this relation will result in no reflected wave. So there's a couple of different ways to go about solving this. You probably won't be surprised to discover that indices of refraction are generally real, and one way to make this thing always be real is to choose your wavelengths and thicknesses, which are represented in K1 and A, so that those cosine terms drop to 0. Cos K1A will be 0 whenever the argument is something like pi over 2, 3 pi over 2, etc., etc. So here's your recipe for making an anti-reflection coating. You have some substrate of index N2. Take a material of index N1 equal to root N2 and slather it on the top with thickness equal to, for example, 1/4 of the wavelength of the light in that medium. So that would be 2j plus 1 lambda 1 over 4, with j set to 0. And this is a thing that manufacturers actually do in practice using a material called magnesium fluoride, which has an N of 1.38 and is very scratch resistant. Granted, 1.38 isn't exactly the square root of 1.5, but it's close and gives you a good result that's very robust and is very cheap to implement. There is a ray optics interpretation of what's happening here, and that is basically that we are setting the thickness here to be such that when some light comes in, travels that thickness and bounces, and travels back, it will have gone half of a wavelength, meaning that it will be 180 degrees out of phase with light that reflected off the first interface. And so the two sources of reflected light will cancel out. That ray optics picture is a bit of a kludge though, because you really have no way of knowing whether the two reflected amplitudes are going to be the same. Are you going to get partial cancellation? Are you not? What are you going to do about the fact that you have some bits of light that reflect like 17 times before they make it out? But the wave optics approach that we took is immune to all of that, because we're not talking about this reflection or the 5th reflection or the 17th reflection. We're saying here are the net fields in each region without attributing them to this or that cause. We do it all in one go, all rolled up, and get a legit answer. And what it's telling us is that if we satisfy the condition established previously, we will get perfect cancellation and 0 reflection. However, we're only going to get that 0 reflection for the one specified wavelength. And last I checked, most light is made up of more than one wavelength. So if you have a simple magnesium fluoride on glass coating, you're only going to be able to get strictly 0 reflection for one wavelength, or one color. Adjacent colors in the spectrum will show more reflection. That issue isn't too bad if you don't have a terribly high demand application. It'll generally manifest itself as sort of a violet sheen on coated optics, since violet is pretty far from the color for which the coating is optimized. Similar principles lead to many kinds of iridescence in nature. Drop a little bit of oil onto water and it'll immediately spread out into very, very thin layers, but those layers will have variable thickness. The air to oil to water layer structure is exactly what we just got done modeling. And different points on that structure, with different thicknesses of oil, will suppress or enhance different reflected colors. When the lighting is just right, it can be quite striking, until you remember that you're looking at some water that got oil dumped into it.